Okay, if we start with the first question, which most people found quite straightforward, it was simple use of I equals Q over T. The total charge is simply the number of electrons, which we're told in the question, multiplied by the charge on each electron, which you should be familiar with by now. So we've got 7.5 times 10 to the 15 electrons, and the charge on each electron is 1.6 times 10 to the minus 19 coulombs, and the time it takes for those to flow is 40 seconds. So if we pop our numbers into there, we end up with 3 times 10 to the minus 5, which of course is answer C. So 1 is C. Okay, moving on to question 2 then. You may remember when we discussed what causes resistance, we drew a little diagram which looks something like this. That represented a wire, like so. And then we said we got positive ions within the metal. My stylus is letting me down a little bit here. Okay. And it was the collision between the stylons, the collision between the ions, the positive ions, and the electrons, which cause resistance. Okay, if you remember that, great. Those positive ions are created by the fact that in a metal, the metal atoms, if you like, bond metallically, so they lose electrons and you end up with free electrons like that. So we therefore have answer D. The copper metal had lost an electron to form positive ions and free electrons, so 2 is D. Okay, moving up to question 3. This was trickier. I'm going to take a little bit of space on here to do this. It's very hard to look at that and come up with a solution, so what you have to do is to draw it in a more familiar fashion. So if I draw my 2 points, oops, let me switch back my pencil there. Okay, so if I put point X here and I put point Y here, then I draw my 2 ohm resistor, which you can clearly see in the diagram goes between those two there, like that. Okay, so if we can get 2 in there, yeah, okay. Right, now, so we've got this bit up here on the diagram already drawn for us. If we now follow the path here, like that, we have a 2 ohm resistor, this one here, connected in series to a second 2 ohm resistor, and then it goes to point Y. So effectively we've got 2 2 ohm resistors connected in series, like that. And this is where my drawing skills need a little bit of assistance. So that is 2 ohms and that is 2 ohms, but we've still got this one here to deal with. Now if you notice, it's actually connected in parallel to this resistor here. Okay, so the second of the 2 like that, we can put in another 2 ohm resistor like that. Apologies, it looks a bit messy this, but hopefully you can get the gist if I just extend that out like that. Oops, I'll just extend that out like that. You might be able to see that a little bit more clearly, so I'll rub that out. There we go. Too much rubbing out. Okay, so effectively we've got that circuit there to analyse. Now the next step is to simplify this little section here, this parallel section here. Well, you've got a 2 ohm resistor in parallel with a 2 ohm resistor, and remember that little trick about calculating total resistances of resistors in parallel? If they're the same, you simply half the value. So effectively this little network here becomes 1 ohm. So then we've got up here, we've got our 2 ohm resistor in parallel with a 2 ohm resistor and a 1 ohm resistor. So this whole circuit simplifies to this. So there's our initial 2 ohm resistor, and then in parallel with that we've got the 2 ohm one from over here, and we've got our 1 ohm one from there connected in series. So you've got 2 and 1, of course, is 3. So you've effectively got that, and you're all well capable therefore of working out the resistance of those two in parallel. So let's just do that then. So remember, it's 1 over Rp is equal to 1 over 2 plus 1 over 3. Lowest common denominator is sixths, so we've got 3/6 plus 2/6, which of course is 5/6. But remember, it's 1 over Rp, so Rp is simply 6 over 5, which of course is 1.2 ohms, which gives us answer B. So question 3 is answer B. Okay, let's have a look now at question 4. Again, this caught quite a few people out. About half of you got this, half of you didn't. So let's go through this. Let's make it a little bit smaller so you can see the question. Okay, so we've got to determine a ratio for the power in X divided by the power in Z. Okay, well the first thing noticed in that circuit is, if we assume that the current going through Z is I. Now because X, Y and Z are all the same value resistor, that current is going through one resistor. The current going through here has to force its way through 2. So hopefully you can see the current going through resistor X is in fact I. Oh, let me rub that out. Let me undo it actually. It's I over 2. Okay. So once you've got that, and one other thing, the fact that power in a resistor, one of the expressions that we use is power equals I squared R, then we can start to look at this ratio. So the power in X is equal to, well, we're saying the current flowing through X is I over 2 all squared multiplied by R, and the power in Y is I squared R again. This time the current is I, and the resistance is the same as the value for X, which is R. Oops. Like that. Okay. Okay, let's put our division symbol in then, because it's the ratio that we're after there. Then that, hopefully you can see, I over 2 all squared is I squared over 4 multiplied by R on the top, and on the bottom it's just a nice, oops, I forgot to put that in there, it's just simply I squared R. Now hopefully you can see therefore that the R's cancel, the I squareds cancel, and therefore you're just left with a ratio of 1 over 4, or 1 to 4, which is answer A. So question 4 is answer A.